Let's look at the hypothesis test for a mean using a table. Here's the idea behind hypothesis testing. We have a hypothesis, which is a guess about what is true. We collect data to test the hypothesis. We plug the data into a formula and then use the result to determine whether our hypothesis appears to be true or not. For example, we've been told that mean body temperature for healthy adults is 98.6 degrees Fahrenheit. But is that true? Let's first find null and alternative hypotheses. The null hypothesis always means no change, no difference, and we represent it with this symbol. Looks like h sub 0. We usually call it h naught. The null hypothesis has an equal sign, so it's going to be of the form mu equals such and such, because again, this is a hypothesis test for a mean. There are other hypothesis tests. We'll talk about those some other time. This is a hypothesis test for a mean. And the alternative hypothesis is that there is a change. There is a difference. We represent this with h sub a or h sub 1. So the alternative hypothesis, h sub a, either has not equals or less than or greater than. So in other words, it's going to be the form mu does not equal mu 0, or mu is greater than mu 0, or mu is less than mu 0. So here, our null hypothesis is that the mean body temperature for healthy adults is 98.6 degrees Fahrenheit. Notice, no change, no difference, what we've always believed, nothing radical, nothing to see here. Keep moving. We're going to represent that symbolically as mu equals 98.6. So let's figure out what the alternative hypothesis is. H sub a would be mu is less than 90.6. We would choose this as the alternative hypothesis if we wanted to test the hypothesis that the mean body temperature for healthy adults is less than 98.6. We would choose this, mu is greater than 98.6, as the alternative hypothesis if we wanted to test the hypothesis that the mean body temperature for healthy adults is greater than 98.6. We would choose this, mu does not equal 98.6, as the alternative hypothesis if we wanted to test the hypothesis that the mean body temperature for healthy adults is different from 98.6, not equal to 98.6. Or if we wanted to test the hypothesis that the mean body temperature for healthy adults is 98.6. So whether you say that your hypothesis is that it's 98.6 or that it's not 98.6, this would be your alternative hypothesis, and your null hypothesis would be that mu equals 98.6. Okay, we're going to choose this as the alternative hypothesis because we want to test the hypothesis that the mean body temperature for healthy adults is 98.6. And if you don't believe me, just look at what I said earlier in the video. So we're going to let y equal the body temperature for healthy adults in degrees Fahrenheit. Sometimes we use x, so I'm going to use y over here. The null hypothesis is that mu, in other words, mu sub y, is 98.6, and the alternative hypothesis, h sub a, is that mu does not equal 98.6. We want to do a hypothesis test for a mean. Do the data satisfy the required conditions? So here are the conditions from a standard stats textbook, DeVoe, Velleman, and Bach. So we have to have a random sample. The sample has to be less than or equal to 10% of the population. Otherwise, it's not really normally distributed or doesn't have a t-distribution. The distribution is messed up. Also, the distribution of the data has to be nearly normal. So when n is less than or equal to 15, we're good as long as the distribution is unimodal, symmetric, has no outliers, is not skewed. When n is between 15 and 40, we're good as long as it's unimodal or more or less symmetric. And when n is greater than or equal to 40, we're fine, as long as it's not extremely skewed. And if there are outliers, we should try eliminating them. Okay, so here are our null and alternative hypotheses. A sample of 106 body temperatures of healthy adults yield a sample mean of y bar equals 98.20 degrees with a sample standard deviation of s equals 0.62 degrees. I did not make these up. These are from an actual study. Calculate the test statistic t equals y bar minus mu sub 0 all over s over square root n. So here, mu sub 0 is the conjectured value of mu in the null hypothesis. In this case, that is going to be 98.6. Okay, so let's calculate the test statistic, t. T is going to be y bar, which is the sample mean, 98.2, minus mu sub 0, that's the conjectured population mean from the null hypothesis, that's 90.6, over s. S is the sample standard deviation, that's 0.62 over square root n. So in this case, that's square root of 106. And that turns out to be negative 6.64, which raises the question, what does that mean? This is what a normal distribution looks like. We would use this if we knew the population standard deviation, because this is what the distribution of x bar would look like. Well, we don't have the population standard deviation. This is what the distribution of our test statistic t equals y bar minus mu sub 0 over s over squared n looks like. It's also called the student's t. We're using this because we don't know the population standard deviation. So notice there are lots of different t distributions, and it all depends on something called df, which stands for degrees of freedom, which is n minus 1. In this case, that's 106 minus 1, or 105. So we have 105 degrees of freedom. So notice when we have a small sample, let's say the degrees of freedom is 1, we're going to get this blue curve over here. And at the other end of the spectrum, when the degrees of freedom is 30, we're going to get the one that's really close to the top curve, which is just a standard normal curve. So the greater the sample, the closer the t distribution is to just a normal distribution. Compared to the normal distribution, the t distribution is a little fatter in the tails. So you can especially see that with this, with this blue one over here. Less so with the other distributions because they're very close to the normal distribution. As n approaches infinity, the t distribution approaches the normal distribution. With a hypothesis test for a mean, when the alternative hypothesis is two-sided, that means we reject the null hypothesis when t is too far to the left or too far to the right. So again, we know this is a two-sided hypothesis because our alternative was that mu does not equal such and such, right? So if that's our alternative hypothesis, h sub 1 or h sub a, that means we're going to reject if we get a t-value that's too large or a t-value that's too small. That's what we mean by a two-sided alternative hypothesis. So again, we reject the null hypothesis when t is too far to the left or too far to the right. In this case, we didn't say anything about a level of significance, so the default level of significance is alpha equals 0.05. That means this area plus this area together, added together, is 0.05. And so we're going to reject our null hypothesis if our t-value ends up in this zone over here. So we need to bear in mind that alpha equals 0.05 because we weren't told anything, so we're just going to assume that. That's the default. It's two-sided. We have a two-sided alternative hypothesis. And our cutoff also depends on the degrees of freedom, which is n minus 1. In other words, 106 minus 1, or 105. So let's look at the t-distribution table. We can find it in the textbook. It's a table in the appendix of our textbook. Here's our textbook. If you're also using MyMathLab, just go to MyLab Statistics, Pearson eText, then choose Table of Contents and Appendices. Or to be honest, you can just enter t-distribution table into a search engine like Google, and you'll get one. They all look pretty much the same. So here's a t-table from a previous edition of a previous textbook. Okay, so the column, notice what we want here. We have a two-tail probability, and the two-tail probability is 0.05. In other words, the stuff on the left and the stuff on the right adds up to 0.05. So this is the column we want, folks. And the row is going to be, the row is degrees of freedom. That's n minus 1. That's 105. So the row is based on the degrees of freedom. So we need to go to the next side of the table. Here's where we are. So here's where we end up with 105. Notice there's no 105 row in the table. So we just play it safe, okay? What we do is round down. So we're at 105, we just play it safe and round down. Even if we were at 119, even if we had 119 degrees of freedom, we would not round up to 120. We would just always round down when it comes to degrees of freedom, just to play it safe. So we have degrees of freedom is 100. We're in this column over here, right? Because it's two-tail test with a 0.05 level significance. So it looks like t star is 1.984. Here's where we're going to use that. So if the alternative hypothesis h sub a is this, mu does not equal mu sub 0, that's what we've got, then the rejection region looks like this. So it's going to be t is less than negative t star, t is greater than negative t star. Since our alternative hypothesis is two-sided and of this form, mu does not equal mu 0, we reject the null hypothesis if t is less than t star or t is greater than t star. From the table, we saw that t star is 1.984. Thus, we reject the null hypothesis if t is less than negative 1.984, in other words, we're out in this zone here, or if t is greater than 1.984. So in other words, if we're in this zone over here. Here t is negative 6.64. That's way less than negative 1.984. We were going to reject if we had something less than negative 1.984. We're way out here, so we definitely reject. We conclude that the null hypothesis is false. We reject the null hypothesis H0. There is sufficient evidence to conclude that the mean body temperature for healthy adults is not 98.6 degrees. Find the p-value. What's the p-value? This is short for the probability value. It's the probability that we would get a result this extreme or even more extreme if the null hypothesis were true. Here's how we calculate it. Just use this table. If the alternative hypothesis is of this form, mu does not equal mu0, that's what we've got, the p-value is twice the area to the right of the absolute value of t. Okay, so what we want is twice the area to the right of the absolute value of t. This is our t, so the absolute value of negative 6.64 is just 6.64. So we need to find the area to the right of 6.64. What's that area? Well, fortunately, our TI can help us out. So on the TI, go to Dister and choose TCDF. Enter TCDF A, B, DF. A in this case is the lower limit, so we want the area that's to the right of 6.64. That means the lower limit is 6.64. B is the upper limit, so that would be infinity. Well, we don't have an infinity button on the calculator, so you could just enter something ridiculously large, like 10 or 100 or 1,000 or whatever. And then DF is the degrees of freedom, which in this case is 105. So when you enter that, here's what you get. You get 7.0974 times 10 to the negative 10th. P-value is twice that, so double it, and you get 1.419 times 10 to the negative 9th. So that's our p-value, or if you wrote it as a decimal, this is what you'd get. You get 0.8 zeros and a 1419. If the p-value is less than alpha, which in this case is 0.05, we reject the null hypothesis, because there is less than a 5% chance that we would obtain a result this extreme or even more extreme if the null hypothesis were true. So we're definitely going to reject because our p-value is much smaller than alpha. So again, one way to remember this, if the p is low, the null must go. When your p is less than alpha, you reject. Reject the null hypothesis. So we reject the null hypothesis because the p-value is so small, there is strong evidence that the mean body temperature for healthy adults is not 98.6 degrees Fahrenheit. Now, if the p-value were big, like 0.25, then we'd say there's not sufficient evidence to reject the null hypothesis. But there is plenty of evidence to reject the null hypothesis here. By the way, the highest body temperature, the highest human body temperature ever recorded was from Willie Jones back in 1980, not the country star, different Willie Jones, man who had heat stroke and whose body temperature was 115.7 degrees. He recovered and left the hospital after 3 weeks. Amazing.